Welcome everybody to today's webinar on commercial building design within RESA. Today we're going to be taking a look at a number of different programs, as there's a variety of different options that RESA has to get commercial building design, or just building design in general. So when we take a look at the list here, today we're going to be taking a look at the latest versions of RESA Floor, RESA 3D, and RESA Foundation, which you can see are 701, 1101, and 501 respectively. And these updates, the 01 updates, were to add compatibility for the bottom two programs that I listed here, RESA Connection version 3, and our second release, the V2 release of the RESA Revit 2013 link. Now, I should also mention that Revit 2014 is right around the corner here, and our Revit 2014 link will be released shortly along with Revit from Autodesk. But in the meantime, we'll work with the Revit 2013 today. Now, with respect to today's webinar, we're going to be talking about a few different topics here, and the first is going to be how to create a building model. And we're going to take a look at various ways of accomplishing this, either creating one from an existing Revit model, or if you don't have Revit and you prefer to work in AutoCAD, we can take a look at how to bring CAD drawings into RESA to create the model. And lastly, we can take a look at how we can build a model from scratch within RESA. Now, in all three of these cases, we're going to be using RESA Floor as our primary program, since RESA Floor is designed to do building design. Now, this is as opposed to more unusual structures or industrial structures which don't conform to a building type of layout, that being a layout where you have generally vertical columns and walls supporting floors, multiple floors in a building. That's what we're going to be taking a look at today. Now, of course, once you create the model, you need to be able to analyze and design that model. So we're going to take a look at all the different phases of the analysis and design of the building. Of course, there's the gravity and lateral, but we're also going to take a look at some of the sort of tertiary or secondary aspects of building design, such as connection design and foundation design. And then lastly, we're going to take a look at how we can take our calculations and construction drawings out of the program. Because, of course, it doesn't do you any good to have a design if that all just exists on screen. You need to be able to communicate that to a contractor or an architect as to what your final design is, and you need to have a good calculation package as well to sort of back everything up, especially if code officials are looking for that. So to start with, what we're going to actually take a look at here is we're going to take a look at an existing Revit model that I've created, and we're going to bring that Revit model over into RESA. So let's look first off at this Revit model that I've created, which is just a single floor of perhaps an odd-shaped commercial building, where we have some bearing walls, we have some columns, and this whole system here that you can see is made out of concrete. And so in this case, I've created a series of concrete columns, concrete walls, and beams. And if I click on one of these columns, we can actually go in here and take a look at its analytical properties. And you can see that on the Revit end, I can set whether or not I have fixed or pinned end releases. I can set whether this column is part of the lateral force resisting system or just holding gravity loads. Similarly, on the walls here, I can come in and I can set, what is this wall made out of? In this case, this is, just a generic 12-inch wall, concrete beams. So I just have some sort of generic sizes set for everything in the Revit model here, and we could presume that maybe you already had your Revit structure model built or that you built one based off of an architect's model. But in this case, for the first floor of the building, we're going to take a look at how we would do commercial building design starting from Revit. So in my Revit model, once I have everything set, I want to make sure that I have the RESA Revit link installed. Now, that's a free download from our website, so you can go on there and download it. And what that does is it adds this extra button into Revit, which is Export to RESA. And it also adds an Import from RESA button. So if I come on here and say Export to RESA, it's going to ask me whether we're going to export to RESA Floor or RESA 3D. Now, for building design, RESA Floor is definitely more powerful, so that's what we're going to want to go with here. And I'm just going to leave all the rest of the settings basically the same here, and I'm just going to export out to this folder. So I picked a path for that. And when I hit OK, Revit, using the RESA Revit link, is going to take all of this information and send it out to RESA. Now, before it sends it over, it's going to give me a little report, and it's going to say, hey, a little bit of model cleanup had to be done in order to get this model into RISA, and that's pretty typical that sometimes some joints won't quite align, and so it'll do that cleanup. But otherwise, we get a nice little summary here that shows everything that was sent over into RISA Floor. So now RISA Floor launches, and we're in version 7 here. And the first thing that it's going to pop up here is the global parameters. I'm going to hit OK and exit out of there just so we can take a closer look at this model that I've got going on here. So let's come up and take a look at a full model view of what we have. You can see that it pretty much matches what came out of Revit. Now the slab that was on here, if I just sort of set that to be transparent, you can see that gets brought over as a slab edge. That's that blue line in the RISA model. And here all the walls and beams and columns and everything else has come over. This is how we're going to handle just the first floor of this building, is as though we brought it in from Revit. Well, certainly Revit has a lot of information, but it doesn't have all of the information necessary to analyze and design a building. So there's a few things that we need to go in and tweak. For one thing, if I come in here and take a look, we can see that we have a deck that got brought over from Revit, and that would be this sort of concrete slab that runs around here. And this was brought in with the definition of 6-inch concrete. And so I can come in here and I can modify what exactly does that 6-inch concrete deck mean. Well, I can come into my deck definition spreadsheet within RISA Floor and tell the program, yeah, 6 inches is good, but I'd like to use 4,000 normal weight concrete. This is some information that the Revit model may not have had stored in it. Now, I'd also like to make sure under the Loads tab here that this is set up to do a two-way load attribution, and indeed it is, and that's what was set up in the Revit model. So we're good to go on that one. The next thing we want to take a look at is the walls. So if I take a look in my wall panel spreadsheet right now, I can see that this is set up to use concrete walls, but it thinks that these walls are going to be CMU. Well, in RISA, we would consider that to be a masonry wall, but I actually want to do concrete bearing and shear walls for this model. So I'm just going to come in here and tell the program that I want those walls to all be concrete, 4,000 PSI normal weight, and I want them all to be 12 inches thick. And so then when I say apply these settings to all the walls, now all these walls in here become 12-inch thick concrete, 4,000 normal weight. So we now have the walls set up the way that we want them to be. The same thing goes for the columns as well. There was a material that was set up in Revit that was called Revit Cast-in-Place Concrete. Well, that really doesn't have all the information that we need to get a column design. So I'm going to come in here and clarify to the program, no, I want all of those columns to be using 4,000 normal weight concrete as well. So I'll just apply that in there, and sure enough, now all the columns are set up to use that correct concrete. So a lot of times when you go back and forth between RISA and Revit, it's important that you come in and you modify some of these materials to make sure that all the properties are present. Because remember that Revit is set up primarily to do BIM and drawings, so it doesn't always have everything that you need to get a full analysis done. The same thing goes for the beams here. I'm also setting all those beams up to use the 4,000 normal weight concrete. So at this point now I have this floor set up the way that I need it, and there's really nothing else I need to do. So you can see that it's very quick and easy if you have a Revit model to get your building design set up and going. But I understand that not everybody out there is using Revit, and so let's take a look at a similar example where we use AutoCAD instead. So in this case, I have an AutoCAD drawing here. And in this AutoCAD drawing, what I've done is modeled all of my beams as line elements. I've modeled all of my columns as blocks. And so in this case, this is a block right here where the center point is where the center of the column is. And my walls I've modeled as a polyline. And the thickness of that polyline I have set to be what the wall is. And you also note that the beams I've put on a beam layer. The walls I've put onto a wall layer. And the columns I put onto a columns layer. Now, you probably, if you're going to start out in AutoCAD, may have a much more complex drawing that the architect gave you or the such. And so you may need to actually shut off some of the layers that are in there, or you may need to tweak certain things. If your wall is drawn as lines representing the inside and outside faces of the wall, you may need to go in and draw a polyline where the center line of that wall is, because that's the only way that RISA is going to be able to read that in. But once you get everything all set up, it's fairly easy to read into RESA. Now also note that in this case, I have all my beams set back about 12 inches from the center line of the beams that they intersect, or of the columns. Well, that's going to be important to notify RESA when we import that we have that setback on there. Otherwise, it will just terminate the beam right here, and that beam will be floating in space over near the girder. So coming back into RESA Floor, I'm going to go up to the File menu, and you'll note that we have under Import this DXF file option. And I've saved my AutoCAD drawing already as a DXF file. So now when I go to Import DXF file, I can point right to that file. And when I open it, it'll ask me a few questions. There's the scale factor and the units, which I can just leave set as 1 in inches because I set my drawing up to be in inches, which is the default for architectural drawings in AutoCAD. I'm going to tell it in this case that my floor elevation is going to be at 30 feet. The beam standoff, that's the distance that I have the beam ends standing off from members that they intersect. And I've got that to be 12 inches. And there is a tolerance in this, so you don't have to have everything exactly at 12 inches. That's just the maximum distance. Now, when I come in here for beams, it's going to ask me which layer of that AutoCAD DXF are the beams on. Well, those are on the beam layer. I have my columns on the column layer. I have my walls on the wall layer. And if I had grid lines for this project, I could also bring those in. But in this case, I don't have any of those, so I'm going to tell it don't bother importing anything for grid lines. Now, this checkbox down here, ignore framing support for beam layer, I get questions about this one occasionally. If this box is checked, then what the program's going to do is bring these beam ends in literally exactly where they are. And so all these beams would be floating, and you'd have this big disconnect, and the whole model would be unstable. But if I uncheck that, then what the program is going to do is it's going to come in and make sure that each beam is supported at both ends by something, and it's going to consider that end offset distance. And that's the way that we want to do it for an AutoCAD drawing that's drawn like this. If I had drawn all the beams so that they snapped all the way to the intersection points, then I would want to tell the program, no, you can ignore how those beams are supported and just use the literal lines that are in the drawing. So with this all set up, I'll hit OK. And what happens now is we've now created an additional floor in the model that is based off of that AutoCAD drawing. Now you'll note that these two lined up in this case. That's because in order to set this presentation up, obviously it's not realistic that you're going to be bringing in both AutoCAD and Revit. I made sure that the X, Y, and Z coordinates between the Revit model and the AutoCAD model that I created were all aligned. So now at this point, when we bring it in from AutoCAD, you'll note that there is certain information that can be gleaned from the AutoCAD model, but obviously not nearly as much as we can get out of the Revit model. So the AutoCAD model, for example, didn't really know what material any of these members were made out of. It didn't know what the thickness of the walls were. It didn't know whether this is a gravity or a lateral. It doesn't know a lot of that information. So when we import from AutoCAD, there's a bit more work that we have to do to come in here and set everything up. But we'll go through that right now so that you can see an idea of what's involved in modifying a model once you bring it in from from AutoCAD. So the first thing I'm going to do in here is come in and give this a proper name. So we're going to call this the third floor, and this is under the floors spreadsheet in RESA Floor. I'm going to tell it to go ahead and use the office area load. Now we're going to take this as a steel floor, and so I'm going to put this in as a composite deck, so that way we can get a composite steel design for this. We're going to come in and set up the splices. I'll say that the splice on these columns will be 14 feet below the floor level. So in other words, the steel columns will be spliced right at the top of the concrete columns. And I'll come in here and set up a shear splice. So this implies that the base plate, where the steel column sits on top of the concrete columns below, is only set up to transfer shear and not moment. That'll be fine for this design. Let's go in for a moment, because we're going to be using steel, and take a look at the global parameters here. I can set my global parameters for this model, and these will affect all sorts of things behind the design. In this case, in order to speed up the analysis, I'm going to reduce the number of sections in here, and that's just an analytical setting that we can do. That's to keep you guys from having to wait too long while you're watching this webinar. Under the Codes tab, I can come in here and pick out my code for each one of my materials. So in this case, let's say that we want to use the AISC 14th edition LRFD for this design. We want to do that for both the steel members and for the connections on the ends of the steel members. For wood, we're going to use the 2012 NDS, and that's going to be an ASD, and we'll see how we can work with both ASD and LRFD within the same model. For concrete, we'll use the 2011 ACI concrete code, and for masonry, we'll use the 2011 strength code. So this building that we're designing here is going to be fully IBC 2012 compliant. I'm going to come in here. We can review a couple settings for composite. In this case, I'm going to adjust my beam deck parallel angle. This is one of the more advanced settings, but when we have members that aren't exactly orthogonal with each other, sometimes you need to tweak a few of these settings to get a full composite design out of it. And so in this case, I had to tweak that setting so that it can design this skewed beam, because of course the ribs are going to be running east to west in this building on my rib metal deck, but the beam isn't really running perpendicular or parallel to that. So it's just a tolerance setting in this case. Now let's go in and modify the walls in this one. Currently what you can see is that these wall panels were brought in as what's called a general wall. And with the general wall, we can't get any sort of design, but I do want to get a design on these walls. So I'm going to come in and tell the program to make all these masonry walls. We're going to tell these are lateral walls, which means that they're going to act not only as bearing walls, but also as shear walls. And so I'll set that up to apply to all of these walls. So now at this point, we have masonry walls sitting on top of concrete walls. Is it realistic? Not necessarily, but the whole point behind this webinar is to show you all the different options for building design. So this may not be the most realistic building you'll see, but I want to make sure that we cover all the different bases behind the commercial building design within RISA. So now at this point, when we came over from Revit, if I take a look at the full model view, you can see that all the openings that existed in the Revit model came over into RISA. However, when bringing something in from AutoCAD, this is just a 2D AutoCAD drawing, and that's how we import from AutoCAD into RISA 3D, into RISA Floor is just 2D for the floor levels. So we don't have any information about what those wall openings may be. What we can do, though, is we can enter that information in directly within RISA Floor. So all I need to do is double-click on a wall here, and this is going to pull up an elevation of this wall. And I can come in down at the bottom, and I can give it dimensions to give me snap points for windows. And so now at this point, I can come in and draw windows in using the Draw Openings tool. And you can see that on a masonry wall, whenever I draw an opening, it automatically places a lintel above that opening. I'm going to go around the perimeter of this building here, and I'm just going to put in some snap points so that I can draw in windows on all these walls. Certainly, we want to be realistic and capture these effects, because the windows in the walls are not only going to affect the way that the reinforcement is laid out, but they're also going to affect the lateral stiffness of the wall. And in this case, we're going to be having a rigid diaphragm on this floor, what with it being a concrete composite deck, and so I want to make sure that these walls all have the correct rigidity. Well, why is that? If we take a look at the layout of the building that I've got here, you can see it's sort of an unusual layout. And so we're going to get some torsional effects, and by torsional I mean torsion of a twisting of the entire building due to the fact that the center of rigidity of this building doesn't exist at the same location as the center of mass. And so the loading for both wind and seismic is going to be offset. Well, the solver within RISA 3D is going to be able to pick up those effects, but in order to get the proper load distribution using finite element analysis, we need to make sure that we've got the proper rigidity in here, hence the importance of putting in all of these windows and openings. Now at this point, I've put openings all around the perimeter of the building, and we can see that reflected on there. That'll take care of that. The next thing we want to take a look at on this floor are all of the columns. So we can see that what the program did is brought in all of the columns from AutoCAD as just plain gravity-only wide flange columns. I'm going to come in and tell the program that I actually want all of these columns to be acting as part of the lateral force resisting system. And we'll see why once we get up to the roof of this building. But for now, another thing I want to do is set this bay up right here as a moment frame. In order to do that and have it be effective, I need to have those columns rotated so that they're going to be facing their strong axis to that beam. So we can just come in here, using the modify columns and rotate these columns by 90 degrees so that now they face each other. At this point, it's important to set up the complete lateral force resisting system for this floor. I've mentioned already about how we have the masonry shear walls over here, but let's say for the sake of complexity, so that you can see all your options in the program here, let's go with a dual system. We're going to have a dual system of both masonry shear walls and steel brace frames and steel moment frames. Once again, probably not a very realistic layout, but the idea behind this is to get a look at how everything works in here. So I'm going to start off by setting up these beams as lateral beams, and we're going to say that'll be a braced frame, that'll be a braced frame, this will be a moment frame, and this will be a moment frame. So now these 4 frames are identified in such a way that when we go into RISA 3D later to get the lateral design of this building, these beams will be brought over, and the program understands that these are important for the stiffness of the building, for our stiffness solution. I'll come back in here and furthermore tell the program that I want my 2 moment frame beams to have fixed ends as opposed to pinned ends, which is the default. And I'm also going to tell it that those moment frame beams are non-composite because, of course, if they're fixed end, they're going to have some negative bending along their length, and so we won't be able to take advantage of that composite action. With that being set, let's also take a look at the materials in this case. So when we brought everything over from RISA, or over from AutoCAD, what we see is everything came over as just an A36. Well, in this case, I want to use a stronger steel, so I can come in, and just the same way as we modified the columns that came in from Revit, we can also modify everything that came in from AutoCAD. So we can come in and graphically say, all right, for all the columns, I want you to change the material to be A992. So I just click OK on that, and I'll do the same thing for the beams as well. We can come in and set all these beams up to be using A992. Apply to all selected, and now all of the beams in this model are all A992 wide flanges. And most of them are set up to be pin-pin strong axis orientation. So at least the program got that part out of the way for us. Now, for the exterior of the building, what we're seeing is these wide flange columns came in by default, and I don't know about you, but I wouldn't want to have to bother doing a connection of this beam into this wide flange column with it oriented that way. What I'm going to do is put a different column type in here to make it easier to get our connections. In this case, I'm going to come in and I'm going to pick out an HSS pipe. So that's going to be an HSS round shape, and I'll put the correct A500 grade 42 on there. And what that'll do is that will allow us to make easier connections on the outside of the structure. Now, I'll be able to come in and weld a shear tab to all 3 sides of this column and be able to connect shear connections to all those beams accordingly. So some of these things that you may not have to deal with immediately, such as how you're going to do your connections, are things that you might want to think about earlier on when you're laying out your project, so you don't have to go back later on and change your columns to be something that the fabricator or the detailer might be more concerned about. Now at this point, we have all these members set up. I'm going to come in and I'm going to add a rigid diaphragm all the way around the perimeter of this structure. And I'm going to punch a couple of holes in that diaphragm as well. And you'll note that on the second floor, those were already punched through because these holes existed in the floor system within Revit. But in here, we don't really have a way to bring in diaphragms and openings from AutoCAD, so I just have to come and draw them in here. And these openings are going to affect not only what the composite design of this beam is, since the effective flange width is cut out, but it's also going to affect our lateral distribution, because now the diaphragm has a hole in it, and so that affects where our center of mass is going to be. And it can also affect, certainly, centers of rigidity, depending on how I've got lateral systems arranged within the vicinity of that hole. All right, the opening is all set. So now at this point, I've got 2 full floors done, one from Revit, one from AutoCAD. Now you'll note that the AutoCAD floor took longer to do than the Revit floor, certainly. Let's take a look at that third option we discussed, which is creating a model from scratch. So I'll go up to Insert Floor within RISA Floor, and we're going to come in and call this one the roof in this case. And for the roof, we'll make it a copy of the third floor, but I want to do a different framing system up on the roof, so the only thing I'm going to copy up are just the columns in this case. I'll set the base elevation for the roof at 44 feet, And I'm going to give this a roof load with a wood decking on there. Now when I hit OK, all it's brought up for us to the roof are just the columns that we had from the floor below. One additional thing that we have available to us, though, are the nodes from the floor below, which also got copied up. You may not be aware of it, but within RISA Floor, we do actually have nodes that are behind the scenes that are connecting everything. This is one thing that makes RISA Floor a bit more powerful than some other similar commercial building design softwares, as you still have the ability to come into spreadsheets and move things around if you don't want to do it graphically. Certainly, graphical modeling is very fast to do in a lot of cases, but there are occasions where having the power of the spreadsheets in there can be something you really want to take advantage of. Now, in this case, what I'm going to do is I'm going to delete a couple of the columns that got brought up from the floor below. And when I do that, the program's going to ask me whether I should just be deleting the column at this floor or all the way down. In this case, I'm going to tell it only delete it at this floor. I want to do this as a wood floor, and so I'm going to want to have some wood-bearing walls. So let's just come in to Draw New Walls. And under Draw New Walls, I can pick out my wall material. And let's say we'll do this wood southern pine, and these would be lateral wood walls, so they'll be taking shear loads within my structure. And I can just draw this node to node if I like. So I'll come around and draw the walls in similar to how they were in the floors below. We'll drop those in, and these will also act as bearing walls for all the roof members that are going to be sitting on top of them. Next, I'm going to put in some members. So I'll shut off the display of nodes so that I can just draw column to column. That'll be the easiest way to do that. I'm going to come in to Draw New Beams, and we're going to draw wood beams. Now, I could draw these as wood dimension lumber, but I'm going to have some rather long spans. So instead of going with dimension lumber, I'm actually going to go with the glue lam in this case. And so I'll pick a 24F 1.8E Southern Pine glue lam, and we'll say that these glue lams are going to be part of the lateral system, and we'll see why before too long. I can just go around and draw point to point. Now you can probably see where an advantage comes in working in this 2D environment within RISA Floor. If we're drawing within RISA 3D, one of the difficulties that we may face is the fact that in RISA 3D we have this wide open 3D modeling environment, which is great to be able to model anything in the world that you want to deal with. But one of the downsides to dealing with that huge wide open 3D environment is sometimes it's tough to see the trees through the forest, as it were, in that you're taking a look at your entire structure all at once when you really just want to be focusing on one floor level. Now, there are ways of getting around that in RISA Floor, but in RISA 3D, but occasionally they can be a bit tedious to deal with. So instead, by working in RISA Floor, I can quickly move from floor to floor and ensure that I'm only modeling on those. Let me draw in some ridge beams because we're actually going to do a slightly complex sloped roof for this structure. And so I want to make sure that I have beams wherever the ridge exists. Now here I've run into a bit of an issue that I want to draw this beam along the ridge, but as you can see, I don't have any snap points that are set up exactly where it needs to go. Well, this is where I'm going to take advantage of some of the more unusual drawing features within RISA Floor. So if I come in and draw, you can see that under that Draw Beams dialog box, we had this set up draw point to point. But there are other ways I can draw as well. So in this case, let me draw beam to beam. So I'll tell the program I want to start with my first beam. I want this one to be offset 0 feet from the end of the first beam that I click on, and that I want the beam that I draw to be at an angle of 0 degrees relative to the beam I'm drawing from. In other words, this beam is going to be parallel to the beam that I started on. So when I click Apply now, I just have to click on the end of the first beam and the beam that it's going to rest on. And that puts it in as parallel to that one, automatically creating a new node right there exactly where I needed it. So that's a rather handy tool to use. Now at this point, I do want to add in some wall openings to match the floors below because, like I said, we need to consider the stiffness. And even in wood walls, stiffness can play a major role in how much force each wall is going to take. So I'll come in and put some openings in. And you'll see that very similar to the way the masonry walls are done, the program puts in a wood header at the top of every opening that I put within a wood wall. So here you can see these headers are laid out. I'm actually modeling more or less the entire building within RESA Floor. That's one of the things that you do within this program is we do the building modeling because it's much easier to do in this case. And we're going to be able to get our gravity design, and then we're going to go into RESA 3D later on and add some lateral members such as steel braces, which is something that wouldn't affect the floor design of the building, but is certainly going to affect the lateral design. And we'll see how these two programs sort of interact with each other in this case. So I'll continue going around and putting the openings in here. Now, had I had a floor that was identical or similar to the floor below with respect to the way that the walls are done, I could have just copied these walls up, and then I wouldn't have had to have drawn these openings in. But because I had masonry on the floor below and wood on the floor above, which, as I mentioned before, probably not a very common design methodology, this is going to be, we have to do things in individual steps on each one of these walls. Now, if I double-click on one of these walls, you can also see that for wood, we get design method options. These are the design methods that are prescribed in the NDS code. So we can either do a segmented, perforated, or forced transfer around openings. Just for kicks, let's put this wall in as perforated, and I'm going to take this other wall over here and set that one to be forced transfer around openings. And we can see how that affects each floor. Next, I'm going to come in and infill all of my rafter members or my purlin members on here. So I'll come in to generate infill beams. This is a really handy tool that's available only within RESA Floor, where I can come in and say that I want to set up some Southern Pine glulam members at an equal spacing not to exceed 4 feet. And when I box this floor here, it's automatically going to put those members in at no more than 4 feet on center within every bay on here. Now at this point I have all of that laid out. What I also want to do is come in and modify some aspects of those roof beams. Now I'm going to actually set all of the roof beams in this case to be lateral. You may look at it and say that that's not necessary to do because I've got, in this case, these lateral walls. That's going to be handling all of the shear in the building due to my wind and seismic loads. However, remember that we also have wind load on the roof. We've got an uplift or a downward load on those roof rafter members. And we want to make sure that these are set up to handle those loads as the wind is blowing sort of up and down on the roof, not just in a side-to-side manner. So I want to come in here and modify this so that all of those members are now set up as lateral members. Now, in addition to this, I'm going to be sloping these members. And if I slope them, that means that there's going to be some axial load that gets carried by each rafter. And certainly a typical wood beam isn't set up to be able to handle very much axial load unless we have blocking. Now I do plan on putting blocking in, but it would be very tedious to model each individual piece of blocking on this wood roof. What I can do instead is come in and effectively tell the program that I have that blocking. I'm going to do that through the Beams spreadsheet under the Wood tab, where here I can set my LE2 value. Now you might be wondering, what does LE2 mean? You might be wondering that about a lot of different things within the program. One of the handy things in the program is that we have a help file that's set up to be able to tell you about anything that you're looking at. So in this case, if I'm wondering what is LE2, all I need to do is hit the F1 key on my keyboard, which I'm doing right now, and that pulls up a help file all about the wood design parameters. And if I scroll down just a little bit, we get a handy informational picture here which shows me what LE1 and LE2 are. So in this case, it's showing this wood member as sort of a column, but if we picture this as a rafter instead, the LE2 is what is the unbraced length in the weak axis direction. In other words, what's going to keep this purlin or this rafter member from kicking out sideways, versus the LE1, what is its bracing in the strong axis direction. The blocking is going to be affecting the weak axis buckling of this member, and so that's going to be an LE2 value. If we assume that we're going to have 4 foot on center blocking all over this roof, then what I can do is come up and highlight this entire column of LE2. I do that by clicking on the column header, and if I right-click within any spreadsheet in the program, I can choose Fill Block. What the program will then ask me is, what value do you want to be filled in on all of the blocks that are selected? And I'm going to say 4. So when I hit OK, it's now set the unbraced length for all those members to be 4 feet. It's a very quick and easy way of getting that set up within the program so that we get some reasonable designs out of these members. Now, another thing to note, if I go back and turn on the node display for a second, you can see that there's a lot of nodes that got copied up from floors below that aren't necessarily relevant up at this floor level. But what I can do with those nodes is clean them up by going up to the Tools menu here, and you'll see that there's a cleanup tool up here that's called Delete All Unattached Points. And when I click that, it'll go through and clean up any extra junk that's basically floating around in the model. And a lot of times within RISA Floor, I like to do that to make sure that everything's looking good. And actually, by doing that, I noticed that I have an issue right over here where I have this beam that appears to be floating in the air. However, I can tell just from the pullback distance on here that it's actually connected to that member. But you certainly want to eyeball things in any floor before you solve it. So let's go in and go ahead and put a diaphragm up on this floor as well. In this case, I'll start out with this being rigid, even though it's going to be a wood diaphragm, because what we can do later on is we can toggle between flexible and rigid, and we can see how that affects the analysis results within the building. Now I've got my entire building laid out, but I do want to have a certain slope on this roof. You can see from going to the full model view that this is a flat roof, not very realistic for a building like this. So let's go in here and let's slope that roof. So I'm going to come in and select certain portions of the roof. I'm going to do this using the selection tools that are at the left side of the screen. And if I just come across and select a portion of the roof, I can then use the roof sloping tool and tell the program that I want this to slope up to a max height of 6 feet above the base height. And then if I just click a couple of points on here, we can see it slopes that up. So next I'll come along and do that for the other portions of the roof as well. In this case, we're going to slope that up from this ridge line right along here. And I'll just grab each successive sloping portion of the model. Let's go over to a plan view to grab this next one here. You can see you can jump back and forth between any different selections. And so now if I come in here, I also want to have that portion of the roof slope upwards. And then lastly, I'm going to grab the bottom portion of the roof right over here, and we'll have that slope sort of upwards and outwards also at that 6 feet. So what we get is a sort of zigzag roof slope on here, but the program is going to be able to do a full analysis based off of this, and it's not only going to affect the length of some of these members, but it's also going to affect the way that the wind loads are handled as well. So let's come into the load combination spreadsheet, and I need to create some load combinations for this building. At this point, we've gotten everything modeled. So I'm going to come in, and I need to create strength level load combinations. That's going to be for my concrete, masonry, and steel design. And then I also need to come back to this load combination generator and tell it I want to do the 2012 IBC ASD combinations. And those are going to be for my wood members. So in this case, I have 2 sets of load combinations. And if I come under the Design tab, what we can see, this is the Design tab of the load combination spreadsheet, by the way, is I can tell the program which load combinations apply to which materials. So we can see these ASD combinations down here. Well, those aren't going to apply to steel, so I can uncheck steel for those combinations. Similarly, those aren't going to apply for our masonry design either. And so I can come in here and control for each one of these, what is this load combination used for or not used for? And then once I've got that all set, I can go ahead and solve my model. So I'll just hit the Solve button up at the top. What's happening at this point is the program is doing a full finite element analysis of this model. And this is going to be an iterative analysis method. So if you look in the lower right corner of my screen here, you'll see solution iteration. And it's going to count up through a number of iterations for each floor level. What's occurring is, you may note that we didn't give the program any sort of starting sizes on here. And so the program is just going to start off with relatively small members. It's going to solve and see what passes and fails. It's then going to upsize members as necessary in order to get them to pass or fail. And once it finishes all of this, then it'll come up with a list. And what we'll see in this case is I've got one roof span warning where my deck is spanning a little bit farther than maybe it should be. and that's all right in this case. And then we can also see that I had a few different members that failed, and we can go back and take a look at what some of those are. For now, let's take a look along the building height and see how things turned out. What we can see down on the concrete floor is that here we've got these members, an 18-inch by 8-inch wide member. And if I click on a detail report, you can see this parabolic shape for the loading. That's showing you how we have that two-way load distribution. We can see, based off of the FEA that was done on this member, the exact deflections that were on there. And you'll note that this isn't just a typical parabolic deflection diagram, because in this case we have some unusual loading and stiffness on there. Here's the moment of that concrete beam. Coming down a little bit farther, we get code checks for the top bars and the bottom bars, and we can see in this case that the code check of 0.941 means that this is almost failing due to negative bending. So those top bars may be basically at their limit, whereas the middle bars there at the bottom aren't really stressed so much, and the shear isn't too bad either. And coming down a little farther, I can get now here a layout on this beam where we can see it's suggesting one number 9 bar at the bottom, 4 number 7s at the top on the left, and 4 number 6s on the top at the right. So we could go in and modify or tweak anything we wanted to on this beam, but at least now we know sort of what that design is going to be. Moving up to the third floor here, I can take a look for each steel beam. I can take a look on this W24 by 62, and we can see all the point loads from the end reactions of beams framing into it. I can get all my information on here, and scrolling down a little bit farther here, we can see that for composite bending, we're at 88.9% of capacity. Non-composite was 87. Deflections was 92.6. So here's a beam that's actually being controlled by deflection. And even at that, the program's recommending a 1 1/4 inch camber along this beam. Now I could come in and take a look at some alternate member sizes as well. So here, let's say one of our typical floor beams is a W12 by 16. If I click the design tool and click on that member, I can come in here and take a look and see why wouldn't it pick a W12 by 14. Well, if I choose W12 by 14 out of the list, it runs a code check on the fly for that member and comes in and then tells us, nope, that member fails the bending check in that case. Or maybe we could take a look and see how would a W14 by 22 work in this circumstance. Or what if I wanted to reduce the studs or change the material? The design button over here allows us to do a lot of different what-if scenarios within the program, which is very handy. Now at this point, I could print out my results from RISA Floor using my report printing tools or printing individual spreadsheets. And now I would probably want to move on and go into RISA 3D. And so we do that with the Director tool in the upper right corner. Coming in here, RISA 3D is going to do our lateral design. So it's going to ask us about the wind and seismic that we have. In this case, let's do a design using 115-mile-an-hour wind speed and an exposure category of C. And so right in here, the program is using the ASCE 7 as well as the shape of our building in order to calculate all of the wind pressures, the windward and the leeward, and it comes up with forces at each floor. Similarly, we can do an equivalent lateral force procedure for seismic. And so we can come in here, and if I enter in my SD1 and my SDS and the such, it'll come in and come up with my seismic design. So maybe let's just put in some realistic values, or at least some realistic by California standards values, of 0.4 and 0.2 here. And we can see the program will come in and tell us that we're in seismic design category D. Here's the equation where we came up with those seismic forces, and here's the force at each floor level. So I'll hit OK at this point. This is going to now bring us into RISA 3D. And I'm going to come in and make a couple of quick tweaks on here in RISA 3D just to make sure that we get a rather quick solution in this case, so that way you don't have to sit there and watch this run for 15 minutes, since we've only got about 15 minutes left in the webinar anyhow. So with the model laid out here, what you're going to see in this case is we've brought over all the lateral members from RISA Floor. So you see a lot of those concrete floor beams that weren't part of our lateral force resisting system aren't shown down below. Now that doesn't mean that those members don't exist. Actually, if we go over into a rendered view, I can actually turn on the display of those members. And what you'll see is they're there. All of these gravity members are there and have been there all along. But we just recognize that in RISA 3D, certainly if you want to come in and do lateral design, having all these extra gravity-only members hanging out in here is going to get in your way. So the program just filters them out of the display by default so that you don't have to have them in your way while you're working on all this. Now let's come in, and on that steel floor, you can see I have this wood wall sitting on top of a steel beam, and if I render it, you can see that more clearly. I'm going to come in and I'm going to put some braces on that steel floor because I want to add some lateral resistance out on this end of the building. So I'll come in to draw new members, and we'll come in here and draw some double angle braces, and maybe we'll go with a 5 by 3.5 inch double angle arrangement in this case. And I'm going to tell the program that this is a double angle with a 3/8 inch gap, so that's going to control what the gusset size will be. A36. It's a V brace, so it's braced in the vertical. It's a brace in the vertical plane, and it's pinned at both ends. And I'm just going to sort of draw these braces in here as chevron braces, right there, and right there as well. And so that will get us our brace layout. Now, another thing that I want to do in this case is I'm going to come in and I'm going to tell the program that I want to get a chevron brace design for the connection at the end of that brace. So I'll come in and I'll tell the program to go ahead and set up the connections to do chevron brace where these two braces intersect the beam. And that way we'll get a design on that one. Another thing that I can do if I'm concerned about seismic is I can also come in and I can set up seismic rules as well. So I could tell the program, hey, these are part of a specially concentric braced frame. And so then if I click on these members, we'll just take a look at the seismic rules, it now recognizes those, you can see, as an SCBF member. And I can come into my seismic design rules and learn, well, what sort of extra seismic checks are going to be done on these braces as part of a SCBF, a special concentric brace frame. Now, with this all set up in here, I'm going to come in and generate some load combinations. So I can come in here, and remember that because we have both ASD and LRFD, we have to generate loads accordingly. So I'll start with my ASD loads, and we'll just go in and set up some wind loads on this model. I'm not going to bother doing the seismic loads since that would take a little bit of extra time to solve, and we just want to get this out of the way. So I'll come in here, set up those wind loads for X and Z direction, and we can see we've got about 27 load combinations that are going to be run on this structure. And I can also come in, just like before, and I can uncheck the hot rolled option by highlighting and saying fill block and filling that with blank so that my steel, say, and my masonry aren't going to be designed using those ASD combinations, and neither will my connections in this case. So I can come in and control how my connections are going to be designed on this structure. With that all set up, I'll go ahead and go in and solve a batch solution. And so the program is now going to go in through here, and with a batch solution, we solve each load combination that's in your model, and we produce the results for each combination. And so this is going to give us the maximum amount of results. This is as opposed to an envelope combination on this structure, where we would only get the results for the worst case load combinations for any given member, as opposed to all of them. But in this case, because I want to run this over for connection design, I want to make sure that I have the results for each and every load combination. And as it goes through and solves here, it's going to be taking a look at that rigid diaphragm distribution at each floor level. It's going to distribute the forces through each wall, figure out the wall force, and then it'll give us a design. So in the walls, in the wood for this case, we're going to get a design of the sheathing and the nailing. For the concrete and masonry walls, we're going to get a design of the rebar. For the steel members, we'll get the code checks and the code checks for the wood members as well. And when it finally finishes with this, we'll have the designs that meet all the lateral requirements of the code so that we're ensuring that this building is going to work for both wind as well as seismic. So after I finish up here, we can take a look. Let's just take a look at the loads real quick that were placed on this structure. One thing that I can view here, this is the dead loads. I can take a look at what were the wind loads up on the roof. And so if we take a look at an elevation of the roof of this structure, we can see what those look like. So here we can see there's about a 10 psf uplift on this portion of the roof and a 5 psf uplift on that portion. Or here, if we switch it so the wind's in the other direction, the magnitudes of these ones change. And as a result of all that, we can actually come in now and we can view how the structure deflects. So maybe I want to take a look at the deflection, and we can see we've got some pretty badly amplified deflection right over there. So some of these members, we may have to go back and take a look at a closer deflection result on. If I take a look at the stress contours, for example, we can see how these walls are affected in terms of stress due to various load combinations. And so we can see here that maybe load combination number 11, which we can take a look and see what that one's all about, that one may be producing a bit higher stresses than some of the other ones. This is dead load plus wind plus live. And so we can see that some of those walls over there were experiencing a bit higher loads. And then, as per usual in RESA 3D, we can pull up detail reports for any members. We can go in and we can take a look at design results in spreadsheets, and we can print any of that out. Now, I'm going to briefly use the Director tool to go over into RESA Connection so we can get the design of the connection for those braced frames. And what's going to happen in this case is we're coming over into RESA Connection and taking a look here, and you'll note that by taking a closer look at the connection design, we can find things that may not have jumped out at us in RESA 3D. For example, that beam that we have that was brought over from RESA 3D, a W16 by 26, I wouldn't have known just from RESA 3D that its flange is small enough that I can't really fit double clip angles on there. So maybe what I need to do instead of using clip angles is switch over to a direct weld so that way the gusset plate is welded right to that beam. Now at this point I can come in and I can do a design based off of all the different end reactions from RESA 3D for both of these brace connections. And so it'll come in here and give me a pass or a fail on them. And I can see in the upper right corner it told me that this passes. I can come in and tweak anything that I want to in terms of dimensions to get this connection to work out. And based off of the report here, I can now come in and take a look and see, well, what's my Whitmore compression block for this connection? I can click on any one of these and it'll expand out and show me all the calculations that are involved. So right here, bolt bearing, this is the equation that was used, and it was based off of AISC equation J36A. So I'll get all my connection information done. And at this point now, I could export that connection information out to a DXF, which we'll go back and take a look at in a second here. And so I mentioned earlier on in the webinar how we need to have a way to get our results out of the program as well, and that's going to be the perfect way to do that. So I can open this up now in AutoCAD, and here's my connections laid out with all that information. You have to remember that it's always important to be able to take the information that's out of RESA and get it into construction documents as well. Let's go back into RESA 3D at this point and now go into RESA Foundation. So I'm using the Director tool to take it over into Foundation. And what we're going to do at this point is we're going to have all of our end reactions from both RESA Floor and RESA 3D, or I should say the column and wall base reactions, are all brought over in here so that we can actually lay out a foundation design. And to do that, I'm going to just snap it into a plan view here. And let's just lay out a few different foundation types. Once again, maybe not a very realistic layout, but in this case, we just want to emphasize some of your different options. So if I come in here, I can draw a slab, maybe, that's going to be over in this portion of the building. So that's going to be like a two-way mat slab. Then coming over on the right side of the building, I'll draw maybe an odd-shaped two-way mat slab as well. And I also want to tell the program that this mat slab doesn't exist right at the edge or the center line of the wall. I want to bump that out some. So I'm going to tell the program to bump out all those slabs by 2.5 feet from where all the columns and the walls bear on them. And so that way we'll have a little bit of extra sort of toe space out around there to spread out some of the loads that are going to end up on them. I'll come in and I'll put in some design strips, and this ensures that I'm going to get a rebar design for this slab. So I'll drop those in right along the perimeter of all the slabs there. And this is going to give us the horizontal direction rebar, and then we also need rebar that's going to run in that vertical or the north-south direction in this case. So I'll draw this in so that we get rebar design for both of those. Coming around the perimeter there, we get that all set. There we are. Now next, I want to put in some footings, so I can come in here under footing definitions, and I can tell the program to drop in some square spread footings that are made out of the 4,000 normal weight concrete. And I can draw those footings in maybe all around the perimeter of the structure. So we can drop them in at any of these locations. And then let's go ahead and throw in some pile caps as well. We'll put those in also using some 4,000 normal weight concrete. And that way I can get pile caps in the middle of the structure so we can see how all these work. And so I can see I can drop in some pile caps in those locations. So with all that laid out and with all the loads brought in from RESA 3D and RESA Floor, at this point now it's just a matter of solving the solution. So it's going to come through and do an FEA solution on all of this, and we're going to get designs for the complete foundation. And this is fully linked into RESA 3D. So as we make modifications in RESA Floor and RESA 3D to the structure, those modifications are going to carry through into RESA Foundation. So maybe this footing, which works right now based off the loads that we've given it, might not work if we increase the dead load somewhat on the structure. Now, similarly, I can come in here and take a look maybe and see how my pile cap design is. We can see in this case we've got a 4-pile layout, and here's all the various rebars that we need. Here's the code check, and we take a look at this here, and we can see with this red number reported, we've got some failures. So we may need to take a closer look at this. Now, I also want to check and see how is my soil doing, so I can come up and view the soil pressure contours. And we can see for the mat slabs in here, right over at these corners, we seem to be having a pressure that's approaching 5 KSF. And I had set this model up by default with a 5,000 PSF allowable soil. So we're getting pretty near that edge range, although I won't be too concerned because usually there's a lot of safety factor in those soils allowable values that come from the geotech anyhow. So with this design all set up, I could come through and I could print out any calculations that I needed from here. I can also export information on, say, the pile caps out to AutoCAD as well. And so this is one of the things that I mentioned, bringing your results out. So let's just export all the information on pile caps out there. And I'll open that up within AutoCAD. And here we can see for each pile cap, I get a detailed output on here, which I can then throw onto my drawings. And soon, you're also going to be able to bring RESA foundation information back and forth to Revit. Although that's not currently in there, it is something that we're looking into. So bouncing all the way back into RESA Floor at this point, if my design's all done, I can also export my RESA Floor information, let's say, out to a DXF file. And so now I can set up all that information. And here I've now brought my building design out into AutoCAD. And so I can take a look at all this information. Here's my camber, my end reactions, my studs, and everything else. But another option I would have from within RESA Floor would be to export this whole model back out into Revit. And in that case, through Revit, if I went back up to my add-ins and said import from RESA, then I could bring all that information back into Revit, and it would bring all those additional floors and all those additional elements in there. I had planned on doing that for this webinar, but as I can see, we're just about to run out of time here, so I'll skip that portion. Now we've got a complete building design for multi-material out of RESA Floor and RESA Connection, and we've gone from basically scratch all the way to that design within a period of about an hour. Now, certainly that's not going to be the end of the story because there's a lot of additional tweaking that needs to happen in here and a lot of checking of results, and maybe we need to adjust some beam sizes and such. But as you can see, when you use these different programs together and you understand how they interact with each other, you can really save yourself a lot of time going back and forth within your design. So I'd like to thank everybody for attending today's webinar.